Uh, Good morning, good day to all. I am Miquéias Cirino. I will talk about my work on the thermodynamics of diluted Ising linear chain with first and second neighbour interactions under an external magnetic field. I am a grad student of Institute of Physics of the Federal University of Alagoas. Our motivation comes from the one-dimensional copper oxides connected with the physics of the high-TC superconducting cuprates that presents a wide number of properties that can be explored by theoretical models. Our group here in Alagoas, with some collaborators, explored these properties like the layer structure presenting these materials in some exactly solved models containing like mobile electrons, competitive exchange interactions, and Columbia interactions. Our model, for instance, is a sawtooth chain with two Ising spins. The S spin represents the copper, and the sigma spin represents the oxygen. We have first interactions between S and sigma that are of ferromagnetic nature because of our motivation, and J2, the exchange interaction constant, mediates the interaction between S and S spins. Our model has some dilution that is inserted by the presence or not of the sigma spin that represents some can represent some effects of doping or impurities in these materials. The Hamiltonian for the if cell of our chain is given by the equation 1. And to connect with the thermodynamics in finite temperature, we wrote down the partition function by the transfer matrix technique. The key point of our model is the dilution fraction. Our chain is divided by unit cells that are triangles, and that in these triangles can be or not be a sigma spin. The dilution fraction tells us that which fraction of the chain has a sigma spin. To finite temperature, the constraint that we have is given by the equation 6. Our phase diagram presents three ground states. In the plane of the external magnetic field versus the radial between the exchanging integrals, we have three phases. In the region where the external magnetic field is strong enough, we have a saturated ferromagnetic phase where all spins are aligned. In the middle of the phase diagram, we have a phase where when we are in a cell without a sigma spin, we have an antiferromagnetic alignment between the nodal spins, S, and it has some consequences because when we build the chain and the chain is built, we cannot connect the cells without sigma with those with sigma, if we not consider that the without sigma cell must appear on pairs. In the region where J2, the antiferromagnetic constant, is strong enough, we have a phase where the unit cell with and without sigma has the nodal spins antiferromagnetic aligned. The dilution in the chain, it these constraints that we have to build it, because the constraints that you have to build it gives rise to residual entropy, because we have a structural disorder in the chain. The physical quantities, because of it, depends on P. For the entropy, we have to calculate the number of accessible states. That is the number of ways that we can build this chain, considering the constraints on the chain. And for the magnetization, we also can calculate it depending on P by the expression in the equation H. In the 9 regions, different regions of the phase diagram, we calculate, we computate the entropy exactly, depending only on P, and its behavior is given by these graphs that shows the dependence of the entropy on P, on the ground state. In the phase, its peak depends on the constraint, where its peaks depends on the constraints. When we have no constraints in how to build these unit cells, how to combine these unit cells, the peak symmetrical, we have its peak in the middle of the graph, but with constraints on the unit cell without sigma, we have its peaks in the left side, and when the constraint is on the with sigma cell, we have its peak in the right side. This behavior is also seen in the coexistence line between phases, where we also see that when we, in these coexistence lines, we have no zero value to the entropy on the edges, P equals 0 or P equals 1, because of the way, because we have more ways to combine the chain. The field dependence of the entropy for different temperatures is shown below, where we have the entropy in the vertical axis and the field in the external magnetic field on the horizontal axis, and the colored dots and lines are exactly calculated quantities. We see the behavior, the peaks of the entropy in the critical fields, and you see that for different values of the dilution fraction, we have a different intensity for the entropy. For the magnetization, we also calculated the exact expression for these values to the J1 and J2 constants. All the behavior of the magnetization is linear. For the dependence of the magnetization with the field, we show that even in finite temperature, we also see the plateaus depending on P for 3 different P dilution fractions. Your conclusion is, utilizing features found in copper-rate oxides, we propose a 1D chain that presents dilution and magnetic frustration. All thermodynamics quantities can be computed exactly in finite temperature and some in the ground state. Considering the structure of the chain, the magnetization and the entropy can be calculated by simple arguments, giving us further knowledge about the physics of the model. Furthermore, we extract the results also for the case where J1 and J2 are of antiferromagnetic nature. I wish to thank the financial support programs, CAPES, NPQ, and FAPEAL, and to all for your attention. Thank you.
Do you have any questions? Maybe we can check questions from the online participants. So you mentioned the motivation from the Q trades. Are there any experiments where people actually are
No,
going to do these dilutions in the spin chain?
there is experiments that has some dependence of the magnetocaloric effect in magnetic material, but that show us that we can find enhanced magnetic caloric effect in these diluted materials, and in these copper oxides we have the magnetic fluctuation independence on the doping that has been explored by some researchers of here at once. So that's why there's a motivation for peroxide.
I see. Very interesting. Any more questions?
I'd like to ask you about working ground canonical or canonical ensemble, because I don't catch it from your presentation.
Okay.
Because you had a fixed number of these.
Yes. We utilized the grand canonical as ensemble to extract these quantities.
Okay, so if there are no more questions, let's thank Miquéias again.